In this video, we're going to introduce the concept of series and parallel connections of resistors. Now, as we've already pointed out, when you've got a voltage source, a source of this electrical potential or this electrical force that is connected in a circuit so that there are conductors running between the source and, in this case, 3 resistors, and then continuing on back to the source, we have a completed circuit, and current then is free to flow. We've also noted that through Ohm's law, there is a voltage drop, or as defined by Ohm's law, there is a voltage drop across the resistor that is equal to the current flowing through the resistor times the resistance itself. So here we've got an 11-volt DC source. It's forcing current or driving current through this circuit that consists of a 1 kilo ohm resistor, 1,000 ohms, a 3 kilo ohm resistor, or 3,000 ohms, and a 6.8 kilo ohm resistor, or 6,800 ohm resistor. It is true that the voltage, there will be a drop in the voltage, a drop in potential across each of these resistors equal to the current flowing through them times the resistance of each of them. Now, to determine the current flowing through here, it turns out that resistors in series, and by series we mean that they have the same current flowing through them. Resistors that are in series with each other can be, the quantities add together, and so we can talk about an equivalent resistance or a total resistance in a series connection that would equal R1 plus R2 plus R3, where R1 is a 1,000 ohm resistor, R2 is a 3,000 ohm resistor, and R3 is a 6,800 ohm resistor. So the total resistance would be 68 plus 3 would be 98 plus 1 would be 10,800 ohms of resistance. The total current then that would be flowing through these 3 resistors would equal the total voltage dropped across them divided by the total resistance. Or again, we're solving this for I, and we get then that I equals V over R, so V total equals 11 ohms. Total resistance we've already calculated to be 10,800, and the current that we would then expect to flow through that then would be the quotient of those two, or 0.001019 amps. Now that's a very small amount of amperage, and when we get into those smaller currents like that, we typically write them in scientific notation, and we'll take this decimal place over 3 units to the right, so that would be 1.019 times 10 to the minus third amps. Or since this is times 10 to the minus third, that's like dividing by 1,000. We'll also refer to that as 1.019 milliamps. The current flowing through this circuit that consists of the 3 series resistances then would be 1.019 milliamps. We can calculate the voltage across each of these resistors then by again using Ohm's law. We now know the current going through the resistor. We can calculate the voltage across this resistor. It's called V1. V1 then is going to equal this 1.019 times 10 to the minus third amps times 1 kilo ohm. Now kilo is 1,000, or like a kilometer, it's times 10 to the third. A kilometer is 1,000 meters, or 1 times 10 to the third meters. So this is times 1 times 10 to the third ohms. Now you'll notice that the 10 to the plus third times 10 to the minus third, the exponents add to give a 0, so that would be 10 to the 0th is 1, and we have then 1.019 volts. As we've already pointed out, this 10 to the minus third is known as milliamps, and this 10 to the plus third is known as kilo ohms. And as we see, when you multiply milliamps times kilo ohms, the millis cancel the kilos, And when we're doing this type of a calculation, we can just use 1.019 milliamps times 1 times 10 to the third, or times 1 kiloohm, gives us then the 1.019 volts. Milliamps and kiloohms are a consistent set of units working with volts, so we would have volts, milliamps, and kiloohms all consistently used together as a set of units. Similarly, we can calculate V2. V2 is equal to this 1.018 milliamps times V2 is the voltage across R2, which is 3 kiloohms. So 3 times 1.018 is 3.056 volts. And finally, V3 then would equal this 1.019. I don't know why I said 018, it's 019 over here. 1.019 milliamps times 6.8 kiloohms, and that equals 6.93 volts. Now you'll notice that, allowing for round-off error, V1 plus V2 plus V3, the voltage drop across here, plus the voltage drop across there, plus the voltage drop across there, will equal the total voltage increase provided by this DC source of 11 volts, or the 1.019 volts plus the 3.056 volts plus the 6.93 volts, again allowing for round-off error. The sum of those three voltages equals the 11 volts. Now another common configuration, another common way of connecting resistances is to have the two resistors connected in what is referred to as parallel. And by parallel, we mean that each of the devices has the same voltage across it. You'll notice that both R1 and R2 are connected to the positive terminal of our power supply, and on the other side they're both connected to the negative terminal of our voltage source. So the voltage drop across R1 and the voltage drop across R2 are both equal to this voltage source here. They both have 11 volts dropped across them. We can calculate I1. I1 is just going to be the voltage across R1, which is 11 volts, divided by 1 kiloohm. 11 divided by 1 is 11. Now we're dividing by a 10 to the third, so that gives us, in the denominator we have 10 to the third, which gives us a 10 to the minus third in the numerator, times 10 to the minus third, or that would be 11 milliamps. And similarly, if we can find a room to do it, the current through I2, the current I2, which is the current through R2, would equal the 11 volts divided by the 3 kiloohms, which is equal to 3.67 milliamps. Now we've got 11 milliamps here and 3.67 milliamps there. The current that's coming from this source then, this source is the source of that current. Part of it's going down here as I1, part of it's going down here as I2. So the total current would be then the 11 milliamps plus the 3.67, or 14.67 milliamps. We're going to learn later on this structure is known as a current divider. The current coming in, some of it's got to go this way, some of it's got to go that way. All of it has to be accounted for. You can think of this something like water coming to a couple of T's in a pipe. Part of it comes this way, and part of it goes that way. But the total amount of current leaving has got to equal the current entering the connection.